coming in during prime time today to take the quiz from Friday.
Okay. We might have a pretty empty class today.
Oh yeah, because you don't have an advisor, right? Oh no,
No.
there's AP exam.
Yeah, the AP test today, I suspect will be half our class. But that's okay.
What AP exam is it?
Language
Oh yeah.
and I think maybe physics in the afternoon, which might be 1 or 2 people. I don't think we'll have many people here today. If y'all want to, if you don't like your angle to the board, you're welcome to move to a different seat today.
What are the AP tests today?
Applac.
Oh, yeah, it's Applac.
Yeah, Applac's the big one, and I think physics. Okay, so we are starting the last part, or the last big piece of what we will have time to do this year, and that is graphing rational functions. So again, this is a topic that came up in Algebra 2, so the more of that you remember, the easier this will be. But most of this is not too difficult, but it can be quite a bit of information. But usually it's fine as long as you remember a little bit of it from Algebra 2. But today's handout is 110, and we won't come close to finishing this one today, but we will take the notes we need to take and things that you didn't remember and make that as convenient as possible. We'll go through the first 5 questions together, and then I'll ask you to do 6 and 7 for homework so that you have a little bit of practice. So when we say rational functions, rational doesn't really mean fraction, but basically that's how it's used. So if you look at all the functions that we're going to answer the same questions about, are functions one big fraction, are functions one big fraction, etc. Ask the same questions over and over, and then using that to help us figure out what the graph looks like. Now, of course, this would be no calculator, because you could just type it in your calculator and get a ton of this information. We're trying to analyze these functions and understand why they work the way they work. Okay, so the first one that I like to start off with is y-intercept. That's usually one of the easier ones. So like all algebra stuff that you ever do, if you want to know the y-intercept, plug in 0 for x and solve. And that's usually pretty easy to do. Even without a calculator. So let me show you the first 4, and then I'll let you try it on 5 before I share the answer with you. And then at that time, if you want to elaborate, you want to add an example here, you think that you need more, you need to reword it, then I certainly encourage you to do that. You don't have to have your notes word for word the same way as me. Okay, but question 1, if I plugged in 0 for x, I get 1 over 0 plus 0 minus 18, so negative 1/18. And for when we get to the graph here in a bit, I'm just going to go ahead and put that point on my graph as well. Number 2, plug in 0 for x, you get negative 2 over negative 4, which reduces to 1/2. I'm going to go ahead and plot that point too. Number 3, we get 0 minus 0 minus 0 divided by 0 minus 0 over 18. 0 divided by 18 is 0. So as I said, the arithmetic's not too bad. You just really have to remember to plug in 0 for x. As long as you know that, it's not a problem at all. Okay, number 4, I get 0 plus 0 minus 6 over 0 minus 0 minus 12. So negative 6 over negative 12 reduces to 1/2. Okay, so go ahead and plot those and quickly do the same thing with question 5. And any of these, even if you don't feel super comfortable, force yourself to make the best educated guess that you can. Write something down. Okay, so question 5, you plugged in 0, and then what happened?
It does not exist.
Okay, how do you know it does not exist?
Because you can't do 4 minus 4.
Right, or negative 4, depending on where you put it.
Yes.
Yeah, can't divide by 0, so if it's not possible, that means this guy's not going to have a y-intercept. Now, of course, you shouldn't just leave it blank. If you leave it blank, it looks like you don't know. Say none, or NA for not applicable. Okay, so now would be the time, if you don't think that is enough of an explanation for how to find y-intercepts, feel free to add or adjust that. But for me, that's enough, so I'm going to box it off and get ready for the next ones. Okay. The next one, we're going to do 3 of these guys at once because the definitions and how we find these are almost identical. And that's going to be X-intercepts, holes, and vertical asymptotes. Okay, so similar to y-intercepts, if y-intercepts is when you plug in 0 for x, x-intercepts when you plug in 0 for y, but you don't have to write this part down unless you think it's helpful. But if you're talking about a rational function, plugging in 0 for y is going to look like this. Well, when does a fraction equal 0?
When it's 0 on top.
Right, so x-intercepts occur when only the numerator equals 0. Now, I'm underlining and highlighting the word only there because that's going to make a big difference, and if you get that mixed up, then that's going to be a problem. So I'm going to have to figure out what numbers make the numerator 0, and then those are going to be x-intercepts. Unless it also makes the denominator 0, and instead that's a whole. So wholes occur when the numerator and denominator equal 0. Okay, this time I'm highlighting the word and because there's some overlap here. If a number makes the numerator 0, you should not assume it's an x-intercept, because if it also makes the denominator 0, it's a whole instead of an x-intercept, and it can't be both things at the same time. A whole doesn't exist on the graph. It's an open spot on the graph. X-intercept is a point on the graph, specifically where it hits the x-intercept. And then vertical asymptote happens when only the denominator equals 0. Vertical asymptotes when only, and again, keyword there, only, because if it makes the denominator 0, it could be a vertical asymptote, but if it also makes the numerator 0, then it's a whole instead. So very, very similar type of work we have to do, but if it makes only the numerator 0, x-intercept, both 0, it's going to be a whole, and if only the denominator, it's a vertical asymptote. Now, for wholes, we need to add a little bit more here because, well, I guess for vertical asymptotes, we should probably say something like it's going to be x equals a number because it's a vertical line. That's how vertical asymptotes should be written. Y or x-intercept should be written as a point. And wholes should be written as a point. But this number, so when this is happening, that's the x value of the whole. So like if 3 makes the numerator and denominator 0, 3 is the x value of the whole. But the y value of the whole comes from plugging in the x value into the reduced fraction, or reduced function. Say that. Okay, and so now let's practice this on the first 4 questions so you can see it applied. And then I'll have you try it on question 5, just like we did with y-intercepts, to give you a little test if it's sticking with you or not. Then I'll give you a chance to revise these and add more detail if you feel like you need them. Okay, so question number 1. For all 3 of these things, I need to know the numbers that make the numerator 0 and the denominator 0. Well, the numerator here never equals 0. 1 is never going to be the same thing as 0. You need to have an x for it to change. And the denominator is probably going to equal 0 somewhere, But until I factor it, so factor out a 3, and then factor the trinomial. 3 never equals 0, but x plus 3 equals 0 at negative 3, and x minus 2 equals 0 at positive 2. So there is some factoring for these. But if x-intercepts are numbers that make just the numerator 0, and there's no numbers that make the numerator 0, this guy's not going to ever touch the x-axis. If there's no numbers that make the numerator and denominator 0, then this one's not going to have any holes. And if there's numbers that make just the denominator 0, those will be vertical asymptotes, and those are vertical lines, so x equals on each one. Now, just to kind of keep our graphs up here, all asymptotes, whether they're vertical asymptotes, slant asymptotes, or horizontal asymptotes, we should graph as dashed lines. So let's go ahead and do that. So sure, it's kind of a pain to factor the numerator and factor the denominator and figure out where they both equal 0. But we need that for all 3 of those things, so it does go a long way. And then there's going to be questions like number 2, where you don't really have to factor it. You should be able to see that the numerator equals 0 at 2, and the denominator equals 0 at 4. So is this going to have any holes? No. No number makes the numerator and denominator 0. There is a number that just makes the numerator 0, so that's an x-intercept, and there is a number that makes only the denominator 0, vertical asymptote. So I can't graph a hole if it doesn't have one, but we certainly can graph the x-intercept and the vertical asymptote as a dashed line. So let's go ahead and update our graph there. We want our graphs to be basically done by the time we've answered these questions, or very close to being finished. Okay, so number 2 didn't require any factoring, so that was nice, but number 3 looks like we've got some factoring that we're going to have to do here. The top has a GCF. And after the GCF, it's also got a trinomial. The bottom's got a GCF. Plus the trinomial. Now, you don't need to factor as quickly as me, but you guys will get plenty of factoring practice with these next class. But I did all of that to figure out the numerator equals 0 at 0, 3, and negative 2. And then the denominator, negative 3 never equals 0, so that's not 1. X equals 0 at 0, so that's why it counts. Negative 3 and 2. So if there's any number that makes both the numerator and denominator 0, we'd have a hole. Doesn't happen here. If there's any number that makes just the numerator 0, we get an x-intercept. So 0, 3, and negative 2. And we really should have known this one anyway, right? The origin's not just a y-intercept, it's also an x-intercept. So it's good to see that the algebra is consistent with that. And then any number that makes just the denominator 0 is going to be our spikes in the graph, our vertical asymptotes. So I already had 0, 0 down, but I also know 3, 0, negative 2, 0, x equals negative 3 is an asymptote, and x equals 2 is an asymptote. Especially the asymptotes help our graphs come together quite a bit, so it's nice to have a bunch of those. Okay, one more, and then I want you to try it on 5 to see if it's working out for you. Okay, so to know where this guy equals 0, I'm going to factor him. plus 3 and an x minus 2. To know where the denominator equals 0, it looks like I need to factor out a GCF first. Always do GCF first if it has one, and then factor it more if you can. And so -4 never equals 0, x plus 3 equals 0 at -3, and x plus 1 equals 0 at -1. Okay, so there's two numbers that make the numerator 0. So I'm tempted to say 3 is an x-intercept and 2 is an x-intercept. But that's not correct. Which one of these is not really an x-intercept? Okay, because it's in both lists. If it's in both lists, it's a whole, not an x-intercept. And that's why in your notes I was highlighting and underlining the word only and. If it's in both, it's something else. Okay, but 2 makes just the numerator 0, -1 makes just the denominator 0. So that would be your x-intercept and your vertical asymptote accordingly. Now for the whole, we want to know what point is missing here. So even though it's not a point on the graph, it doesn't exist at that point, we still are required to find the y value as well. So I have factored my numerator, made it look like this. I factored my denominator, made it look like this. So if I'm focused in on this part right here, to find the y value of the whole, you have to plug this x value into the reduced fraction. So the fact that -3 makes the numerator and denominator 0 means there should be an x plus 3 factor. So let those cancel. Reduce your fraction. And then plug -3 into what's left. -3 minus 2 over -4 times -2, which would be -5/8. So you plug in the x value of the whole into the reduced function. If you don't cancel out the x plus 3 and the x plus 3, you're going to get 0 over 0. You got to cancel those first and then plug it in. Okay, so we've got another point, which was the x-intercept. We've got a new asymptote, x equals -1. And even though it does not hit the graph at -3, -5/8, we still need to put it on our graph as an open circle, as a hole. So put a hole here. Okay, and again, you kind of have to work multiple of these questions to really know if you can do them all correctly, because it's not possible. Well, I guess it is possible to have all of them, but most questions don't have x-intercepts and vertical asymptotes and holes. But go ahead and try question 5. See what you think you get, and then we will check it, give you a chance to adjust your notes, and then we will move on to domain. Okay, so the numerator never equals 0, Negative 4 is never the same thing as 0. And the denominator needs to be factored for you to be able to see that it's 0 and 3 that makes it 0. And then again, there's no substitute for knowing the rules, but if you know the rules, usually there's not much work here. The factoring is most of the time the most work you have to do for any of these. So nothing makes the numerator 0, nothing makes the numerator and denominator 0, and 0 makes the denominator only, and 3 makes the denominator only. So that's what you should have gotten for those 3. So can't graph an X-intercept if it doesn't have one, but I can put in our vertical asymptotes. And of course, make any corrections you need to for that, and feel free to adjust your notes on the box on the top page. Okay, next in our list of things to describe is domain, and domain still means the same thing as it's always meant. It's a way to describe the x values of the function. And now in most of these functions you can plug in basically any x you want to. So instead of us trying to figure out what x values we can plug in, we just do the opposite of that. We try to figure out which x values can we not plug in. Well, I don't know if you want to write this in your notes or not, but just so you guys know, there's really like 3 ways to restrict domain ever. One is called implied domain. So like if it was a real world question, and I don't know, maybe it's something about time. Well, we don't let time be negative in those situations. That doesn't make sense. Time being 0 is kind of the left side of your domain. So that's not going to come up in this. Also, when you take the square root of a negative number and you start getting into imaginary stuff, imaginary numbers are not part of domain, because domain implies that we're talking about real numbers. But if you scan through our worksheet today, you can see you're not going to have to deal with that. The other way you have to restrict domain is when you divide by 0. And that's going to come up a lot here. So domain could care less whether it's visually a whole or visually a vertical asymptote. It just knows that you can't plug in that x value. There's not going to be a y value for that x value. So since we've already thought about what numbers make the denominator 0, this won't be too much work. We just got to practice writing our answer out. So what I would recommend that you guys do, at least for a while until you feel more comfortable here. So domain, I can basically plug in anything I want, and I'm going to represent that with the number line. But I can't plug in -3, and I can't plug in 2, because those are both division by 0. But that means I can plug in everything less than -3, which we would write this way. Everything from -infinity to -3, always the smaller number on the left. Then I can plug in these numbers. So also include everything between -3 and 2. Now I'm not including -3 with these because of parentheses. Brackets would be include. I don't want to include. I want to skip it. And I can hit everything bigger than 2. So if you do the number line, you can see where the 3 little sections are coming from. -infinity to -3, -3 to 2, and 2 to infinity. Okay, question 2. The only number we need to take out is 4. So I can plug in everything except 4, which means I can plug in -infinity to 4, but don't include 4, and everything from 4 to infinity. So if you're only taking one number out of the domain, your domain's in 2 pieces. If you're taking 2 numbers out of the domain, it splits your domain into 3 pieces. Okay, number 3, we had two numbers that made the denominator 0, so we need to take out -3 and 2, which means I can plug in everything from the far left till -3, everything from -3 to 2, and everything 2 to infinity. I think that might be the same as number 1, actually. So again, domain can care less what it looks like on the graph. Doesn't care if it's a whole or vertical asymptote, but division by 0 doesn't exist, so it has to be taken out. Okay, one more, and then I want you to try it, and then we can move on. So question 4, it looks like we had two numbers make the denominator 0, which was -3 and -1. So our domain would be -infinity to -3, and -3 to -1, and -1 to infinity. Now, I don't care if you guys do this number line after a few of these, but I do want you to see how it gives you kind of a visual of where all the different parts of domain comes from. It makes it a lot easier. So at least do it until you're super confident. But try question 5, please. See what you get. And we'll check it and move on. So we're only taking out two numbers, 0 and 3. 0, 3. So we should have -infinity to 0. We should have 0 to 3. And we should have 3 to infinity. You guys are familiar with this U symbol for union?
Yes, sir.
Okay. Making sure. Just a math way to say and. Okay, make a correction if you need to there. Feel free to add some details to your notes on the top page. Again, I don't really care what you put in this top box. I just want it to be one place for you to look up if that ends up being something that you struggle with. Okay, so we got 3 more, but the last one's just going to be plot and points, so I'm not even going to make space for that in the notes up here. So really 2 more. And one of those is horizontal asymptotes. Now, luckily we actually reviewed this a couple months ago. Otherwise you would just be trying to remember it from last year. But I can also tell you, if you're signed up for calculus next year, this does help you with a certain type of calculus question where you can basically do it without calculus if you know these rules. But for horizontal asymptotes, you need to compare the degree of the numerator to the degree of the denominator. Which then creates 3 different cases. Because the degree of the numerator could be bigger than the degree of the denominator. Degree of the denominator could be bigger than the degree of the numerator, or they could be equal. That's why there's 3 cases, 3 possibilities here. So what we're really thinking about when we talk about horizontal asymptotes, we're talking about the very far right of the graph and the very far left of the graph. So when x is extremely big and extremely small, approaching infinity and negative infinity. All the rest of the stuff doesn't really matter, but the stuff with the biggest exponent does. So if your numerator has a bigger exponent than your denominator, they're both growing, but if the bigger exponent's on top, it's growing faster. So in this case, you end up not having one. Your graph eventually just shoots up or down, but we'd have to do more work to figure that out. But if your denominator is growing faster than your numerator, just like all fractions, if the denominator is growing quicker, and as x gets bigger and bigger and bigger, it grows way, way faster, it gets closer and closer to 0. So our horizontal asymptote, it's a horizontal line, so y equals, but it would be y equals 0. And if the degrees are equal, then they're basically growing at the same rate. So then what it depends on is the leading coefficient of the numerator over the leading coefficient of the denominator. So like if the numerator has a 5 and the denominator has a 1, the numerator is growing 5 times faster. So it would be a 5. Now, it's kind of a mouthful there to say all 3 of those rules, but it's pretty easy to apply once you know them. So we'll knock out all of these very quickly. So looking at question 1, the degree of the numerator is 0 because there's no x's. The degree of the denominator is 2. And because I know the rules, if the degree of the denominator is bigger, the horizontal asymptote's y equals 0. Doesn't require any more or any less thought. Very to the point. Number 2, looks like the degree of the numerator is 1, the degree of the denominator is 1, so we need to take y equals leading coefficient, which is 1, over leading coefficient, which is 1, and we get y equals 1. These are asymptotes, so I'm graphing them as dashed lines. Number 3, the degree of the numerator is bigger than the degree of the denominator, so it does not have a horizontal asymptote. Question 4, the degree of the numerator is 2, degree of the denominator is 2, so we're going to get it from the leading coefficients. Y equals 1 over negative 4, or negative 1/4. Okay, please try on number 5 before I share the answer with you, just to give yourself some feedback. Okay, what'd y'all get for this one? Degree of the denominator is bigger, so it's always y equals 0. So if you know the 3 rules, those are literally 5-second questions. But if you didn't add that to your graph, please add it to your graph now. And we've got one more asymptote to review, talk about plotting some points, and then how all of our graphs are going to come together. And then it really just comes down to you practicing it enough that you know and can do all these things without using your notes. Okay, the last one is slant asymptotes, also known as oblique asymptotes. In America, we typically refer to them as slant asymptotes, but I think most of the rest of the world refers to them as oblique asymptotes. Also, if you ever participate in a math contest, probably more than a 50% chance they would refer to it as oblique instead of slant, but same thing. And this one can be a pain. The good news is we don't have to do this for most questions. Most questions don't have a slant asymptote. But the first thing you really want to know is when, so that you don't do all this unnecessary work. So these would occur when the degree of the numerator is exactly 1 bigger than the degree of the denominator. So if that's not true, we just say it doesn't have the slant asymptote and move on. So let's actually do that for the first 5, and then we'll come back and we'll talk about how to find it if it has one. Okay, so question 1, the degree of the numerator is not 1 bigger than the degree of the denominator, so no slant asymptote. Again, don't leave it blank, you need to say none. Leaving it blank makes it look like you don't know. Question 2, the degrees are equal, but that's not what it says. It says the degree of the numerator needs to be 1 bigger. So number 2 doesn't have a slant asymptote. What about number 3? 3 will, so we'll have to come back and finish that one. Degree of the numerator is 1 bigger than the degree of the denominator. Question 4, the degree of the numerator is not 1 bigger than the degree of the denominator. Question 5, yes or no?
No.
Degree of the numerator is 0 because there's no x's, and that's not 1 bigger than 2. Okay, so as I said, most of the time they're not going to have a slant asymptote, but of course on our test we will put at least one of them on there so we can be able to test you and see if you know how to deal with it if there is one. So last part of our notes in this box at least, the how you find it is we will have to do long division. We have to long divide them, and our answer is going to be y equals whatever the quotient is. So ignore the remainder. If there's a remainder, it has no effect on the slant asymptote. So, no coincidence that we have reviewed long division recently. Another reason why we need long division. So, within the first 5 questions, there's only one of these that we need to even do that for. And it is a touch harder than normal, than most of these, because it will have some fractions. But I would like to long divide this denominator into the numerator. And my slant asymptote is going to come from y equals whatever the quotient is. We're going to ignore any remainder if there is a remainder. So we know this times this is supposed to give me x cubed. Now on harder questions like this, I usually break this up into parts. Does this need to be positive or negative? Good, because a negative times a negative gives you a positive, like this one. What number can I multiply by 3 to get 1?
1/3.
Good. Multiplying by 1/3 is the same as dividing by 3. And then what times x squared gives me x cubed?
Just x.
Just an x. So again, with the fractions, it's a lot to do in one big chunk. But if you think about the sign as a step, the fraction as a step, and then the x's as a step, we've got our first piece. Okay, so that gives me that. I also need to multiply it by this. Negative times a negative is positive. 1/3 times 3 would be 1, and x times x would be x squared. And then the last part, times 18, negative times a positive would be negative. 1/3 times 18 would be 6, because multiplying by 1/3 is like dividing by 3. And x times no more x's just gives you an x. Please, please, please change the signs and add. And if you can keep going, you got to keep going. So it looks like we could go one more time. So we got to think of the thing times negative 3x squared that gives us negative 2x squared. So again, split it up. Usually you don't have fractions like this, but that's okay. It's good practice. So should this be positive or negative? Positive times a negative is negative. Okay, what fraction could I multiply by 3 to get 2? Well, what fraction could I multiply 3 by to get 1? Okay. Alright, so if multiplying by 1/3 makes it a 1, to make it 2 times bigger, I want it to be 2/3. So positive times negative is negative. 2/3 times 3 is like dividing by 3 and multiplying by 2. And I didn't include any more x's here because I already had x squared. Then multiply it to this. Change the signs and add. And it looks like we're done because this guy here is now the remainder. Remember, remainders don't just have to be numbers, but we can't do the process again without putting x's in the denominator, which is not what we're interested in. So slant asymptote, the remainder has no effect. So it's kind of nice if you make a careless mistake at the very, very end of a slant asymptote question, it doesn't mess you up. But our slant asymptote equation comes from the quotient. Negative 1/3 x plus 2/3.
Could you just stop once you got the 2x squared? Because you knew the rest of it was going to be
Yeah.
the remainder.
I would have, yeah. But it just, the problem is if I do stop there, if you're not sure that the rest is going to be a remainder, or if you assume the rest is a remainder and it's really not, then that would backfire. But okay, so now we got a slant asymptote. Well, we can graph this. All asymptotes need to be dashed lines, and this is in the format of mx plus b. It's got a y-intercept of 2/3 and a slope of negative 1/3. So count down 1 and right 3. Make that a dashed line. So again, kind of a pain, but you don't have to do it on many questions. So make sure you know the process. Long division, y equals the quotient, ignore the remainder. But also know that you only need to do it when the degree of the numerator is 1 bigger than the degree of the denominator. If you long divide all of these, you're going to be wasting a lot of time. Okay, let's go back and finish off these graphs, talk about how to check them, and then again, we're going to do that for the first 5 as we've been doing. And then I'm going to ask that you do at least questions 6 and 7 for homework, because the sooner you start practicing and making yourself review these rules, the sooner they're going to stick. Now, I didn't have you put this in your notes, but of course, plotting a bunch of points is always going to make your graph better. When you graph these in your calculator, it's not really analyzing the rational function the same way you do. It just plots hundreds of points, plots them on the graph, and then it says, here's your graph. Well, for us, you know, I've got this 1 point here, so maybe I'd kind of like to know something over here. So I don't know, I'm not going to pick x equals 10. That's not going to help me with my graph. I'm going to pick something small, like maybe x equals 3. And like all points, just plug 3 into the function. And solve for y. Looks like it is 1/18. So I've got 1 point near the right side of my graph, 1 point somewhere here in the middle. I kind of like to have maybe 1 more point somewhere on the left side of my graph. So I'm going to pick -4 and plug it in. So this would be 3 times 16 minus 12 minus 18. Again, I'm just plugging in this x value into the function and then trying to evaluate. You see, 3 times 16 is like 3 times 10, which would be 30, plus 3 times 6, which would be 18. So 30 plus 18 would be 48. So this would be like 1/18 again. So just a coincidence that those are the same. Now, I don't think we need any more points because I know how these graphs are going to interact around the asymptotes, which I'm about to show you. But I certainly encourage you to always do more points. If you feel like you need more points to feel confident about your graph, then please do. On a test, we'd probably ask that you do like 4 or 5 points, but I think this is going to be plenty. So you need to know 2 things about the asymptotes. For vertical asymptotes, which would be here and here, your graph is going to spike up on one side and spike down on one side. It's going to go to infinity on one side and negative infinity on the other side. If we look at today's agenda, this is what this is kind of referring to. If it goes up to infinity on one side, then it has to go down to negative infinity on the other side. The other thing you need to know is that for horizontal asymptotes and slant asymptotes, the biggest misconception is that you can't cross those. You can't cross vertical asymptotes, but you can technically cross horizontal and slant asymptotes. What they tell you, though, is what the y value approaches at the end of this graph. So I know this point, and I know it has to get closer to 0 the further to the right I get. And I know this point, and it's got to get closer to 0 the further to the left I get. So that's what horizontal asymptotes and slant asymptotes tell you, is what y value it approaches on the far left and far right of the graph. Now, the reason this is so important is if I can see that this is slowly coming up from right to left, it's going to continue this way. And so if I know it has to spike right here, based on this direction it's going, it must spike up on the right and down to the left. Or I could have gone over here and done the same thing. From left to right, it looks like it's going up. So that means it'll keep going up. So this side, it spikes up on the left and then down to the right. And I've got this point that it needs to hit. And now it all kind of comes together. Now, if I had messed something up, my graph would look really confusing because everything just kind of fits together as a puzzle piece here. But if I have some conflicting information, then I know something is off. And I'm going to tell you how to check this with your calculator. Again, we won't give you a calculator on the test because we don't want you to just graph it and then like read off stuff you read from the graph. We want to see that you can analyze it. But let's do the same thing over here. More points is always better. I'm sure we will tell you to do a few more points on the test. But honestly, if you understand how it interacts around the asymptotes, you are basically finished on this question because these points have to connect. It looks like he's going down, so he's going to spike down on the left side of this vertical asymptote and up on the right side. And for horizontal asymptotes and slant asymptotes, that tells me the y value it approaches on the far left and far right. That's a very good estimate. It's not perfect. It's never going to be perfect unless you plot 1,000 points like your calculator does, but it's very accurate for how much time we're spending on it. Okay, number 3. Okay, so, oops. Again, horizontal asymptotes and slant asymptotes tell you what y value it approaches at the far left and far right of the graph. So I could take this point that I'm sure is on my graph, and I know it's got to approach this line on the far right. Which then tells me, hey, if this guy's going this direction, he must spike up on this side and spike down on that side. Then to keep it going, I know it's got to hit this point, and then it must turn around to come back to hit that point. And then based on his direction, he must be spiking down on the right side, which means he's spiking up on the left side. And finally, on the far left of the graph, it's got to get closer and closer to it the smaller x gets. So we'll graph this one in just a minute so that you can see how to check with your calculator. Okay, and then number 4, so one more, and then I'd like you to try question 5 on your own. Again, more points is always good. Plus, if you graph a point and like, if you graphed x equals 4 and it doesn't match up with what you thought the graph was going to look like, that's at least a warning flag that something might be off. But I know these 2 points connect. I know it has to approach this y value on the far right because it's a horizontal asymptote. Based on the direction of this line, he must be going up on the vertical asymptote on the right, so then down on the left. Even though it doesn't hit the hole, it will hit the points right before it and right after it, so that's still helpful. So connect that with this, and it's got to approach the horizontal asymptote on the left. Okay, and actually I lied. I'd rather graph this one because I want to make a point about this hole with your graph. Okay. Is this the equation for number 4? I can't look at both of them at the same time.
Yes.
Okay. So when you practice some of these on your own, again, you're only going to have to do 2 for homework right now. But if you type it in and you look at the graph, you can kind of tell if it looks right. But one thing I would suggest maybe is changing your window settings, because these graphs only go from -5 to 5 for x values and y values. So if you go ahead and change those window settings, just a quick eyeball test, this compared to this, those look the same? Yeah. Looks fine. So if you did something wrong, it's going to look different. It's going to be obvious that it looks different, but it's also going to give you like some ideas of what you did wrong. Like if you only think there's 1 x-intercept and you graph it in your calculator and you see there's 2, then that tells you, hey, you didn't do x-intercepts correctly. So you would need to fix that, update your graph, and then see if it looks okay. But the reason why I wanted to graph this one over the other one that I'd said is we have a hole in our graph right here, right? We indicated that with this big open circle. As smart as your calculators are, they are terrible at finding holes. So right here, it doesn't look like there's a hole in the graph. What's happening is it doesn't exist at x equals -3, but it exists right before it and right after it. And your calculator has to just approximate and decide whether it should fill in the pixel or not fill in the pixel. So more of it should be filled in than not. So there's not this gap here. Now, some newer calculators for some functions will put a little bit of a gap so you can kind of see that there's a hole there, but those are not consistent at all. But to convince you that your calculator knows it and just doesn't show it very well, if you were to hit trace -3 enter to jump to that spot, it understands that when x is -3, y doesn't exist. It knows there's not a point there. It just doesn't have a good way of showing that to you. So even if we let you have a calculator on the test, it would be 0 help for holes. Then the next best thing you can do to check to see if your y value of your hole is correct is you could be at x equals -3. You could go a little bit to the left, see the decimal is about -0.6, or you could go a little bit to the right and see that it's about -0.63. And what did we say our y value of the hole was?
-5/8.
So the graph looked about -0.6 or -0.64, whether you're looking at the right or the left. So negative 0.63 is right there in the right spot. So your calculator just doesn't show it very well. But quick eyeball test, if your graph looks like that graph, then you're probably in good shape. If it doesn't look the same, then at least it should be giving you some indication of what you need to do differently. Okay, so if you would, take a moment to try to finish off the graph on number 5, and then I will tell you what I would have done. And unless you get stuck, I also encourage you to go ahead and throw it in the calculator, see if it looks right, and if it looks right, you're welcome to just move along to 6 and 7. Y'all remember doing some of this last year?
Mhm.
A
Okay.
little bit.
Okay, so on question 5, if you didn't finish there or you were getting stuck, just based on this function, we had 0 points to go with, and we need something to start off of. So I tried not to do as many points because it's a little tedious, but in this case, you needed to start with something. So there's no point in plugging in 0 or 3. We know those don't work, but maybe plug in something like 1. So don't lose this negative sign either. I'm just going to move it up here so I never forget about it. That would be negative 4 over 1 minus 3, which is 2. So our graph should have the point 1, 2. Okay, unfortunately 1 point is not going to be enough here, so maybe I'll try negative 1. So negative 4 over 1 plus 3, which would be negative 1. Now, of course, you don't have to plug in the same points as me, but you did have to plug in some points. You got to have something to start off with. Okay, now part of this graph I think is ready to go, because this one had a horizontal asymptote. I know he's going to approach it on the far left. He's got a vertical asymptote here, and based on the direction of this graph, I know this one's going to spike down and then spike up, and it's got to hit this point that I knew about. But I still don't feel super confident about what's going on over here. And again, one of the biggest misconceptions is that you can't cross a horizontal asymptote or a slant asymptote. If your graph has 3 sections, this certainly can cross here. So this guy could do like this, or he might do like this. And so it looks like I need maybe one more point. So maybe something over here when x equals 4. Minus 12, so that would be -1. Okay, now that I know 4, -1 is a point, and I know it's got to approach this on the far right, which means it's going down here, which means it's going up there, and then I can connect it with this. And then if this was a question you were doing on your own, I'd recommend that you graphing it in your calculator. Okay, so go ahead and finish copying that down if you did get stuck. And now is the best time, even though I tried to give you multiple opportunities today. That box on the top page, any of those definitions, explanations, you need more examples to, different wording to, please do that. Because all of these parts are not that bad, but it is a lot of information. And assuming that, if I assume that you don't remember any of these from Algebra 2, then that's the hurdle you have to tackle. So as you practice these, you should try to maybe start off with the ones you feel most comfortable with. Then at some point, the ones that you're less comfortable with, go and read the notes first, and then try them, etc., etc. But then each question you do, you should be leaning on your notes less and less. So anyway, if you would please at least do questions 6 and 7 for homework. That way your brain is starting to think about these things. Of course, you're encouraged to do more, and we will practice more on this worksheet next class, but 2 at the very least. Okay. Any questions that jump out at you that y'all want to ask?